All right, so we've been talking about work for a while, and we know work is energy. We measure that in joules. And when we now want to talk about, like, how is that energy transferred? We've talked about work, that, we've applied a force, and that force has made a displacement. It's changed how our system is set up. There are a couple different ways for energy to be transferred. We've really only been talking about work. I'm just going to brush upon these other ones really quickly. We have heat. We're all pretty familiar with it. But on the microscopic scale, it's collisions between atoms or molecules. So the more heat something has, that means the more collisions there are going to be. And this is the whole area of thermodynamics. And for example, when a spoon rests in a cup of coffee, the spoon becomes hot because some of the kinetic energy of the molecules in the coffee, because that coffee's hot, so those molecules are moving around very quickly, so they start running into the spoon, and that energy from the coffee is transferred into the molecules of the spoon. So now the spoon has more internal energy, and the molecules in the spoon are moving a lot faster, so they become hotter. So that would be talking about heat. That's how heat transfers energy. And for that to happen, for heat, there has to be a temperature difference. Without that, there isn't any exchange of heat. And just a side note, when it's been really cold outside and you leave the door open because you're a teenager and that's what you do, and your mom yells at you, she's like, "Hey, shut the door, you're letting the cold air in." You're not letting the cold air in, you're letting the hot air out. It goes from high to low, like everything you've studied in nature, like high concentration to low concentration. So when she says you're letting the cold air in, you can be like, "No, Mom, thermodynamics, the hot air is going out." So there, but close the door, conserve energy. So a couple other ways, real quick, to transfer energy. Mechanical waves, a disturbance, that's what we did out in the hallway, like with the slinky, propagates, that means it moves. This means it moves through a medium. So we have sound waves, water waves, seismic waves are earthquake. You've got those P and S waves. S waves you remember from earth science. And then electrical transmission, transfer by electrical current. Again, this stuff all goes from high to low, and this is how electrical energy enters any electrical device. So these are just a couple of the ways that we transfer energy. We're not going to be studying any of these in detail quite yet, but we've got one more, and then we're going to dive into how we will be studying it. So we have electromagnetic radiation, electromagnetic waves, light, microwaves, radio waves. Cooking something in your microwave oven. So that's actually, you have waves of electromagnetic energy that go in and they start vibrating. They heat up the molecules in there and they start vibrating faster, and that's how it heats up. So we'll talk about that later. Or light energy traveling from the sun here to Earth to keep us warm. But what we're really going to be getting into is power, because power is a bit more descriptive. We want to know the rate at which energy transfer takes place. And power is defined as the rate of energy transfer. So this would be, energy is work divided by time. So power equals work divided by time. So the units of that are called watts, and a watt is equal to a joule per second. The same units of work are in joules divided by seconds. So if you want to be more powerful, to have your power go up, there are two ways that you can do that. You can do more work in a given amount of time. So if you're doing more work, you're more powerful. Or what you can do is you can do the same amount of work, but do it in a very small amount of time. That would also make your power increase, because if this starts to go to 0, this number here gets very large, and then power increases. So you should have everything here that's on this slide I want you to have. And we're going to look at an example very quickly. And the example will be from your homework set, number 1, where it says, Atlas, Hercules, and Tabon, 3 carnival sideshow strongmen, each lift 200 kilogram barbells 2 meters off the ground. Atlas lifts his barbells in 1 second, Hercules lifts his in 3 seconds, and Tabon lifts his in 0.95 seconds. Question A, ask which strongman does more work. B, calculate the power developed by each man. And C, which man is more powerful. So we'll start with part A. That makes sense. We want to know which one does more work. And we're pretty familiar with work. So we know that the formula for work is equal to F cosine theta delta x. F is our force acting, theta, cosine theta, that's the angle between our force and our displacement. So we first need to figure out the amount of work that each guy does. The hardest part here is going to be what force is acting here. What's the force? That force for us here in this example, as you're lifting it, what the force is going to be gravity. So that force is going to be the mass of those barbells, which is 200 kilograms, times the acceleration due to gravity. So that's what our force is equal to. So 200 times 9.81, and we get 1962 newtons. There's our force, and we're going to plug this into our equation. That's the force that they're exerting to lift that barbell. And we're going to say that they are exerting that force straight up, and their displacement is also, so there's the force, I'm going to say, and their displacement is also straight up. So what is the angle between the force and the displacement? Well, if they're in the same direction, that means they're parallel, and that means that theta is equal to 0, and cosine of 0 is 1. So let's go ahead and plug all of this into our equation here, so that our work is equal to 1962 newtons times, we'll plug it in, cosine of 0 times our delta x of 2 meters. So we get a work of, our work is equal to 3924 joules. That's the work that each strongman does, because they're each lifting it 2 meters. So to answer part A, which strongman does the most work? For part A, they all do the same. Because they've all lifted the exact same amount of weight, the exact same distance. So they all do the same work, because they're doing everything exactly the same. Now what's going to be different is the power, because we know that they lift this in different amounts of times. Like some of them it's really easy to lift and others really struggle with it. So let's figure out part B. It wants to know the power developed by each man, each strong man. So we know that power is equal to work divided by time. If we know the amount of work and we know how long it takes them, we can figure out the amount of power they have, and we'll be able to figure out which one is the most powerful. So Atlas, it says that Atlas lifts it in 1 second. So his work, we already know, was the 3924 joules. The amount of time it takes him is 1 second. So taking out our calculators to do this, he has a power, develops a power of 3924 watts. Now you could label that as watts or joules per second. They mean the exact same thing. Remember, that's the unit of a watt, a joule per second. So that's Atlas. Then we have Hercules. So Hercules does the exact same amount of work, the 3924 joules, but he does it in 3 seconds. So that's divided by 3 seconds. So right off the bat, you know Hercules is not going to be as powerful because it takes him longer. So dividing this out, we get 1308 watts. So we know that Atlas is more powerful than Hercules, but we still have Tabon left. And we know the amount of work Tabon does, and that is equal to 3924, just like everyone else, joules, and he lifts it up in 0.95 seconds. So this value right here, we have made time smaller. So what do you think? Is Tabon going to be more or less powerful than Atlas? Well, he's going to be more powerful because time is smaller. He did the same amount of work in less time. So dividing this out here, we get that Tabon does 4130.5 watts. So Tabon is the most powerful. Good for him. He's gone to the gym. He didn't skip leg day. All right. So there's our first problem done on the homework. Let's go back to the actual PowerPoint and talk about power. So we know it's work per time, but there's a little bit more stuff I want to talk about at first. So there's instantaneous power as well. And we'll investigate the units of that to make sure that it all fits out. Instantaneous power is, I like to think about it like how much power is a car producing at a moment in time. So the only way for this to work is for the force and the velocity to be parallel. They have to be in the same direction. And this can change with time, but we're looking at it at just 1 instant right now. So another formula for power is force times velocity. So I would have that down. All right. And let's investigate the units of both of these to make sure that they check out. So power, I'm going to go back to this slide right here. So we know we've got power is equal to work over time. And we know that power is also equal to a force times a velocity. So the units of work are joules, but there's another way to write that. There's another way to write work. We can write that because work is F cosine theta delta x. It's a force times some distance. And the units of force are newtons. Distance are meters. And those take care of our units on the top. On the bottom here we have time, so we have seconds. So looking at this, I see a newton times a meter divided by a second. Well, separating this out some, this is the same thing as a Newton times a meter over a second. Hey, a Newton times a meter per second. Is that Newton's units of force? Meters per second, units of velocity. So right there's a quick little check that work divided by time has the exact same units of force times velocity. So that all checks out. So we're good with that. Now let's look at example number 3 on your homework. It says, in an action-adventure movie, Private Ryan lifts the 91-kilogram villain, #forgets-units, straight upward through a distance of 1.2 meters in 0.51 seconds at a constant speed. Now, constant speed is bolded here. What power does the hero or heroine produce while doing this? We can use either equation to do this, but let's go with our power equals force times velocity because I just talked about this as an example, so we'll do that. So we first need to figure out the velocity that this thing is moving. And that's not too hard, because we know velocity is equal to distance over time, and I told you it's moving a distance of 1.2 meters in an amount of time of 0.51 seconds for a velocity of 1.2 divided by 2.35 meters per second. Now we need to determine what our force is, and again we are lifting something, so the force here that we're battling with, that's the force of gravity. So our force is going to be the mass of our object, of our 91 kilogram villain. So our force is going to be 91 kilograms times acceleration, 9.81. So doing this out, we have 91 times 9.81. So 892.71. 892.71 newtons. So we now know our force and our velocity. So we can plug it into our equation that power is equal to force times velocity. So the power is equal to 892.71 newtons times the velocity of 2.35 meters per second. So multiplying that out, we have 2,099.6 watts. So there is our power produced by Private Ryan lifting the villain #forgets-units. So all this stuff isn't too bad. And there's one more thing I want to talk about, and that's just coming from America and how we use our units for this. And generally in America, when we're talking about how powerful something is, we're talking about horsepower. You know, that is my goal someday. I need a car with more than 300 horsepower. But how much watts is that? We have the conversion factor that 1 horsepower is equal to 746 watts. So this is the power comparison to what we are used to using in, you know, how we measure cars or motorcycles or whatever. And then one other subject about it, if you're looking at, you know, your electric bill or the meter on the side of your house, it'll often measure stuff in kilowatt hours, or kWh, and that's units of energy. That's not, even though you see watts in here, that is a unit of energy, because this right here is a kilowatt hour, meaning they are multiplying watts, which have units of joules over seconds. So they're multiplying watts by hours, or another unit of time. They're multiplying joules per second times seconds. So the seconds cancel out, and we're only left with joules, which is a unit of energy. So if you look at your bill, or your parents' bill, when it says kilowatt hours, that's a unit of energy. That's how much energy you've used. Don't confuse that, even though it says watt in the name. That's how much energy you've used in a given amount of time. And we just prove that right there because our units check out. So I hope this helps and you're able to follow through. And good luck with the homework.